Okay, now we are in part C, and we need to be careful here because what is it asking for? We need to identify that clearly, and any numbers that we need, and in units, the conversions are going to be very important again. So part C is asking for tangential acceleration of a particle 60 centimeters from the center when omega is 125 rpm. So if you remember, in the problem was asking for from it start at 200 rpm, it's slowing down to rest, and but this omega is somewhere in between, right? And also saying that particle 60 centimeters from the center is really that radius r, so the particle is somewhere here, right? And then this distance is your r, and we are looking for tangential acceleration. Okay, first, and then part D is going to be radial acceleration for the same parameters as part C. So first, let's find tangential, and then we'll look into radial. So once you figure out which one you're trying to find, you just write the equation. Tangential acceleration is r alpha. We already know what r is, but it's 60 centimeters, needs to be converted to meters. You divide by 100, you get 0.6 meters. And alpha is we figured it out in part A. It was negative 13.3 revolutions per minute squared. However, we need to get meters per second squared for the acceleration, so we need to convert things. Okay, so we need to convert revolutions. Sorry, not revolutions. Revolutions to radians. Yeah, that's the SI unit, and also minutes to seconds. So this first parenthesis is for that revolutions conversion to radians. You do know that 2 pi radian is 1 revolution, right? So in order to get a revolution, you need to put revolution at the top, and 1 revolution is 2 pi r radian, so put the 2 pi r radians at the top. So then you can get rid of revolutions that way, and then minute square needs to be converted to second square, so you are trying to get rid of minute square. Since minute square is at the bottom, you need to put the minutes at the top, and 1 minute is 60 seconds, and square that, so it's going to get rid of, after you apply the square here, you're going to get rid of the minute squares, and everything is going to be in terms of meters per second square. This radian here, it stays, but it doesn't have a dimension, so you don't show it here. Okay, and this unit is pure meters per second square. And again, it didn't matter what omega was, right? It's regardless of that, because it was constant acceleration, constant angular acceleration. So we get the answer to be negative 0.014 meters per second square. Again, it's negative because it's slowing, and it's very, very small. If you compare with the gravitational acceleration, it is 1,000th of g, right? And for the radial acceleration, we have the equation. It's the centripetal acceleration, so we use v squared over r. We've already shown that it can be also written as r omega squared. So what do we have? R is 0.6 meters converted from centimeters, and omega given as 125 revolutions per minute. So for the radial acceleration, omega matters. You need to be given in the value, right? And we are doing a conversion again. First is to convert minutes to seconds. Next is the revolutions to radians, and they are gonna go away. Revolutions go away, minutes go away, and then you're gonna simply get meters per second squared. There's second here, and it's gonna be squared. The whole thing is squared here. So you get meters per second squared that way. And again, after the algebra, you have 85.7 meters per second square. So it was much bigger than g, but we just used that value to kind of approximate. It was hard to get the number, right? Because there's a lot of conversions. It's hard to estimate. but like almost 9g. Okay, so these are the ends. So this is like how you find these, but one extra step is the total acceleration. So it specifically asks you to find the tangential acceleration and radial acceleration. Instead of doing these, like these part 2, it could have just asked you to find the acceleration. It doesn't even have to say total, okay? If it asks you to find acceleration, it means it's asking you to find total acceleration. So instead of asking for part C and D, this is what they could have asked. And in order to find this, you needed to do part C and D. Okay, but I want you to kind of see it. Sometimes it can be hidden like that. Because total acceleration can be found using radial and the tangential acceleration. This should be R, not N. Okay, so radial acceleration and the tangential acceleration. These are the components. Since these two are perpendicular to each other, you can simply do Pythagorean theorem to figure it out. Square them, add them up, take the square root. Since AT is so small, AR is dominating, and you can see that we get the same amount, although in intrinsic fix there's not much change, but if you take more digits you can see the change. They're not exactly the same because we have our AT to be non-zero, but it's so small it doesn't affect much. Okay, but that would be the way to figure it out. You can even find out the angle of the total acceleration for that when omega is 125 revolutions per minute, using the components and everything. So that those are more vector algebra, but there could be more to the problem. And in next class, I'm going to add an in-class problem so that you can also practice those things one more time. So as discussion or reflection, our answers are reasonable based on our initial expectations. It was hard to estimate in this problem because there were a lot of conversions. So we tried to see if we knew that it was negative or positive for the vectors mostly. And again, we see the similarity with the linear motion, and rotating objects can experience significant accelerations. Okay, and we must be careful with the unit. So if you just look at this problem, we get an acceleration as 0.014, but at the same time we get theta to be 1500. So the range of numbers are going to be very different from now on because we have the linear case and the angular, and I think it is a little harder to estimate in these chapters, but it's really still kind of chapter 2, understanding the definitions, and it comes with practice, so you have to do a lot of practice. It may not be very clear. Please go through, like especially those AT, AR equations and such. Really understand where they come from. Next, you will have a couple clicker questions, and that's going to be all for today. On Wednesday, we are going to talk about rotational kinetic energy as well after the in-class problem.